Okay, hi everyone. So today we will learn in our last chapters on chapter 25, which is nuclear physics. Okay, so in nuclear physics you will learn about three subtopics. Okay, important subtopic, which is the first one is nucleus, the second one is radioactivity, and the third one is nuclear reaction. Okay, so today we will cover on nucleus. Okay, so in nucleus subtopic you will describe the discovery of proton and neutrons. I assume that you have 100% no problem with proton and neutrons. Okay, so dah faham sangat lah apa proton and neutron. Okay, and then you will explain about mass defect and binding energy. Actually, mass defect you had learned this in your STPM level. Okay, mass defect and binding energy. Binding energy also you had learned, but we just call it as Einstein equation. E is equals to mc square. So for higher level, these equations are represent the binding energy. Okay, so use the formula for mass energy equivalence, that is delta E is equals to delta mc square. Okay, and relate the use of the units of U and electrovolt. Okay, and then you need to sketch and interpret the graph of binding energy per nucleon. Okay, binding energy per nucleon against the nuclear number. So you need to understand the graph and the equations, okay, to find the value of the what you want to find out lah, whether you need to calculate the binding energy per nucleon or nuclear number or binding energy only. Okay, so we will discuss more later. Okay, so for nucleus, okay, for the introductions of nucleus, so any nucleus is made up from protons and neutrons, and it is known as nucleons. Okay, so this is the definitions of nucleons lah actually. So a proton has a positive charge of +1, okay, E, but a neutron is electrically neutral. Okay, so a specific nucleus nuclide can be specified as A, Z, X. Okay, this is the specific nucleus. Okay, it represents by the symbol of AZX. Okay, where X is the atom. Okay, so A is the mass number of the total number of nucleon in the nucleus. Z is the atomic number of the number of proton in the nucleus. Okay, so Z is the proton number lah. Okay, A is the nuclear number. So the number from this symbol and the value, so we can find the number of neutrons from the equations of N is equals to A minus Z, means that the nuclear number minus with the proton number, so you will get a neutron number. Okay. Okay, nuclei which have the same number of proton but different number of neutrons are known as isotope. Okay, so we dah biasa lah dengan terms of isotope. Okay, so all isotope have the same chemical properties. Okay, so let's unify the atomic mass unit, which is what we call as U. Okay, atomic mass number lah. Okay, So atomic masses are usually measured with reference of the carbon-12 atom, which is a sign of mass of exactly 12 U. Okay, it refers to carbon-12 atom. Okay, so one atomic mass unit is defined as 1/12 times the mass of one carbon-12 atom. Okay, this is the definitions of one atomic mass unit. Okay, atomic mass unit lah. AMU. If you can still remember this unit, okay, on your SPM level, okay, AMU, which is represented by U. Okay, so 1 U is equals to 1/12, okay, of the mass of one carbon 12 atom. Okay, so 1 U is equals to 1.66 times 10 power of negative 27 kilogram. Okay, so to substitute in the equations for EMC square, so make sure that the M is in kilogram. That's why you need to know what is the conversions of unit when you want to change from U to kilogram. Okay, so we can express the mass of the following particles in the unit of U. Okay, mass of proton is equals to 1.00728 U. Okay, neutron 1.00867 U. Electron is 0.0000055 U. Okay, this one no need to remember lah. So when the calculation questions come out, they will give you the conversions lah. Okay, so what you need to know is how to convert only. Okay. Okay, so Einstein mass energy relation. Okay, so one conclusion from Einstein theory of relativity is that energy is equivalent to mass and are mutually convertible. Okay, so the energy equivalent to mass it will be given by the equations of E is equals to mc square. Okay, we known these equations previously as Einstein equation. Okay, which is m is the mass and c is the speed of light in vacuum lah, 3 times 10 power of 8 ms negative 1. So by converting atomic mass number into kg, and when we apply in the equations of E is equals to mc square, so we can show that the energy which is equivalent to a mass of 1 U is equals to 1.66. Okay, it based on this equation lah. Okay, 1.66 times 10 power of negative 27 times with the speeds of light in vacuum lah, 3 times 10 power of 8 power of 2. Okay, so 1 U is equals to 1.494 times 10 power of negative 10 joule. Okay, so we also can convert the joule unit to mega electrovolt. Okay, so if we want to change joule to mega electrovolt, so what we need to do is divide, okay, by 10 power of 6 times 1.60 times 10 power of negative 19. Okay, this is how you want to convert lah. So you had known that how to convert from U to kg. Okay, so from kg, when we substitute into E is equals to mc square, so we get the joule. Okay, the joule unit, right? Okay, so from joule, there's another one more unit that you need to know that can represent by the energy of Einstein, that is mega electrovolt. Okay, so to convert from joule to mega electrovolt, you just need to divide by 10 power of 6 times 1.6 times 10 power of negative 19. So 1 U is equals to 934 mega electrovolt. Okay, so by using more accurate data, we can obtain 1 U is equals to 931.5 mega electrovolt. Okay, so it depends. Sometimes dia bagi 1U is equal to 934. Sometimes 1U is equal to 961.5. So you just refer to the questions that given to you lah. Okay, both are accepted actually, but this one is more accurate. Okay, normally use lah. Okay. Okay, this is the conversions from joule to mega electrovolt. Okay, let's look about the mass defect. Okay, so mass defects is susut jisim. Okay, penyusutan jisim. So before and after the reaction, so there's the difference between the total mass of the reactions before and the reaction after. Okay, so for any nucleus, the total mass of the individual nucleon is always greater than the mass of the nucleus. Okay, total mass of the individual nucleon is always greater than the mass of the nucleus. So the difference between the total mass of the individual nucleons and the mass of the nucleus is known as the mass defect. Okay, this is the definitions of the mass defect. Okay, so please do remember this definition. Okay, for example, helium-4 nucleus is made up of 2 protons and 2 neutrons. Okay, so the calculation below shows that the nucleus has less mass than its total mass of its 4 individual nucleons. So the nucleus has a mass defect of 0.030. Okay, so as you can see here, so the nucleus has less mass than the total mass of 4 individual, the total of 4 individual neutron. Okay, so as you can see, the difference of the total mass of individual nucleons and the mass of the nucleus is the difference, and it is equal to the mass defect, and the difference between this value and this value is equal to 0.03040U. Okay, so the mass defect of 4,2 helium nucleus is given by so this is the calculation lah. Okay, so you have 2 proton, okay, you have 2 neutron. Okay, so this is the value of the proton and neutron lah. Okay, substitute and then minus with the nucleus, so you will get the difference is 0.03040U. Okay, so generally the mass defect delta M can be concluded as this equation. Okay, so delta M is equals to proton number times with mass of proton plus with nucleon number minus the proton number times with the mass of neutron and minus with the mass of nucleus. So according to this equation, you can find the mass defect, okay, for the individual nucleons and the mass of the nucleus. Okay, so just follow this equation. Okay. Okay, so the reason of the mass defect is as follows. Okay. Sorry. So in the nucleus, the nucleons are bound together by a strong nuclear force. Okay, so as work must be done to separate them, they must have less potential energy when bound. Then they would have a free particle. So therefore, they must have less mass. Okay. So the minimum work done to break a nucleus completely into the individual nucleons at infinity, we call it as the binding energy of the nucleus. Okay, and it is given by the equations of E is equals to delta mc squared. Okay, from the calculation above, we can calculate the, from the previous diagram, so about the helium. So we can calculate the binding energy in the helium-4 nucleus as the binding energy is equals to mc squared, so 0.0304 U. Okay, so please to remember how to convert from joule to mega electrovolt. Okay, so when you convert, you will get 28.3 mega electrovolt. So since there are four nucleus, since there are four nucleon in the nucleus, so the nuclear binding energy per nucleon, nuclear binding energy per nucleon, nuclear number lah, E per A is equals to 28.3, the total energy in mega electrovolt divided by the number of nucleon, divided by 4, so you will get 6.08 MeV. Normally the binding energy, we will state the answer in mega electrovolt lah. So for Einstein relation, we state the answer in joule. Because why you need to convert in MeV? Because when it comes to graph, the graph of binding energy per nucleon, so the graph is in MeV, so you need to understand how to convert from joule to MeV. I hope that is clear. So all nuclides have the mass defect, apart from hydrogen 1, whose nucleus is a single proton. So this table shows that the mass defect and the binding energy per nucleon in 3 different nuclei. So actually, as we know, the binding, this is the mass defect of the hydrogen, iron, lead and uranium. And this is the binding energy per nucleon. So this is the value lah. So it already convert from joule to mega electrovolt. So the binding energy is equals to E mc square. So mass defect times with C square. So binding energy sama lah macam the Einstein relation energy tadi. So proton number times with the mass of proton plus with the nuclear number minus with proton number times with the neutron number. So minus with the nuclear number. Mass of this one is mass of neutron, minus with the mass of nucleon. So times with C square. So this is the binding energy equation. So let's see about the binding energy per nucleon, and versus nucleon number graph. So first of all, you need to memorize this equation, that is binding energy per nucleon is equals to binding energy of the nucleus divided by nucleon number. From this equation, so you can find the nuclear number, you can find the binding energy of the nucleus, and also the binding energy per nucleon. So please do remember this equation. So let's see about this graph. What is energy per nucleon? Actually energy per nucleon is required to completely, energy per nucleon are required to completely break up the nucleus. Okay, dia nak putuskan, dia nak pecahkan nukleus tu. Okay, so nucleons are more strongly bound to one another, have high binding energy per nucleon. Okay, so it likely to break up and hence it is more stable lah. Okay, so bila dia ada ikatan yang kuat, okay, dengan binding energy per nukleon, so dia boleh memecahkan rantaian dia untuk jadi lebih stabil. Ini macam nuclear reaction lah, if you can still remember about fission and fusion. Pembelahan nukleus and pelakuran nukleus. Nuclear fusion and nuclear fission. So we will explain more after this. Okay, so from the graph above, it shows that the nuclear binding energy per nucleon with the nuclear number in the nucleus. Okay, so from this graph, we can conclude that the average nuclear binding energy per nucleon is above 8 mega electron volt. Okay, as you can see here, so average nuclear binding energy semua above 8 point, kebanyakannya above 8 megavolt. So the stability of the nucleus depends on the binding energy per nucleon. Okay, so semakin apa tu, kita nak tahu kestabilan nukleus tu adalah depends pada the value of binding energy per nucleon. So thus nuclei in the middle of the periodic table are more stable. So if you can see the nuclei in the middle of the periodic table yang ada kat tengah-tengah tu semua adalah unsur-unsur yang stabil. Okay, for heavy nuclei, the stability of the nuclei decreases when the nuclear number increases. Okay, for heavy, okay, for heavy nuclei. So the stability of the nuclei decrease when the nuclear number increase. So the heavy nucleus like uranium, as you can see here, so uranium is heavy nucleus. So uranium-235, and it will split into two lighter nuclei which are more stable. Dia akan break dia punya break up, dia akan pecahkan kita daripada unsur besar, dia pembelahan, okay, dia belah, okay, so dia pecahkan untuk dia jadi lagi stabil. Okay, so energy must release in this reaction, so for sure dia akan lepaskan tenaga. Okay, this is what we call as nuclear fission. Okay, so dekat sini berlaku fission sebab dia berat. Okay, sebab dia adalah nukleus yang berat, so it will break, okay, to into two or more nuclei to become more stable. So this is what you need to understand. Dulu kita belajar kenapa dia belah je. Okay, now you need to know from the graph. Okay, so kenapa dia belah? Sebab dia ada kaitan dengan binding energy per nukleon dia. Okay, so if the two nuclei fuse together from a heavier nucleus which is more stable, okay, energy is also released, okay, because the binding energy increase. Okay, so dia two light nuclei, dia nuclei yang ringan combine together, okay, to become more stable. Okay, so this is what we call as fusion, pelakuran. Okay, so this is what you need to understand about the graph variations of nuclear binding energy per nucleon with the number of nucleon. Okay, so as you can see here, you kena tahu kat mana yang akan berlaku nuclear fission and di mana nuclear fusion. Apa dia cakap? Kat mana berlaku nuclear fusion and di mana nuclear fission. Macam tu. Okay, so let's try this one. Okay, energy release in the nuclear fission reaction. Okay, so the energy is released, okay, in the nuclear fission reaction can be estimated from the graph as follow. As you can see here, fission occur when two light nuclei combine together to become more stable. But fission, one heavy nuclei, dia apa? Split into two, okay, to become more stable. Okay, so for nuclear fission reaction, okay, as you can see, this is the equation. Okay, so we can find the change in the binding energy. Okay, change in the binding energy is equals to the energy released in the reaction. Okay, so as we know, the binding energy per nucleon is equals to binding energy, dia macam ni lah senang. Binding energy per nucleon is equals to binding energy divided by the nucleon number. Okay, so to find the binding energy, we want to find this one lah. Okay, binding energy kita nak cari ni lah. Okay, this one is represent binding energy per nucleon. Binding energy per nucleon. Okay, so you have the nucleon number here, and then you have my binding energy here. Okay, so you can find the change in binding energy lah. Okay, so we can see from this graph the average of the nuclei to become more stable is in this range. Okay, is in this range. Okay, so this is the range of maximum stability. Okay, so the binding energy is equals to the nucleon number times with the binding energy per nucleon. Okay, so we start with the 92 krypton. Okay, times with the binding energy per nucleon 8.8 plus with barium 141 times with 8.5. Okay, so this is the maximum stability. Okay, before it comes to fission. Okay, this one is the maximum when it start from fusion. Okay, so kita cari kawasan yang dia ada maximum stability. So dekat situ yang kita akan start ambil dia punya calculation. Okay, so minus with the heavy. Okay, this one is the fusion lah. Okay, this one is fusion. Okay, this one with the fission. Okay, so minus with the fission lah. Okay, fission kat sini we have uranium 235 with the binding energy of the binding energy over nucleon. Okay, 7.4. So we will get the change in binding energy is equals to 269 mega electron volt. Okay, so uranium actually has low binding energy per nucleon lah. Okay, so it will making it unstable. Okay, so dia akan jadi unstable. Okay, bila dia unstable baru dia boleh undergoes radioactive decay. Baru dia boleh terus mereput untuk jadi more stable. Okay, so that's all for today. I stop here. So if you have any question, please ask. Thank you.